Greetings to all. A very warm welcome to all of you who are present here. This is Mohammad Junaid from Data Science stream studying at Institute of Aeronautical Engineering. So today I am here to present a PowerPoint presentation on a fluidic colorimetric sensor which is specially designed for the detection of hardness of water. So let's get started. So our topic is a fluidic colorimetric sensor designed for water hardness detection. It means for the detection of water, we use this tool which is known as a fluidic colorimetric sensor. Okay, now let's go for the introduction. A new sensor design for detecting water hardness using colorimetric concepts is presented in this slide. Water hardness is of great concern to both domestic and industrial users. See, water hardness. The water hardness is a very great concern to the both uh, small scale users as well as the large scale users. Okay, for the both industrial purpose also and for the small purpose also, it is a very important concern to them. Okay, and it is caused by compounds of calcium and magnesium and by a variety of other metals. So while detecting the hardness of the water, the calcium and magnesium, they play a major role. Without them we cannot detect the hardness of the water. So the calcium and the magnesium are the major metals, we can say, which are very important for the detection of hardness of the water. Along with magnesium and calcium, we use other metals also. So we'll move to the next slide. Yeah, as the concentrations of calcium Ca plus 2 and magnesium Mg plus 2 are usually greater than other alkaline earth ions group 2. Hardness is equated to Ca plus 2 plus Mg plus 2, 2. So here he is given that as the concentration of calcium and magnesium are usually greater than other alkaline earth metals. So why we consider only the calcium and magnesium as our first preference is nothing but because calcium and magnesium having the more concentrations when compared to the other metals of the alkaline earth metals group, which is in the periodic table. We know that the first group and second group consist of all metals. Okay, in those two groups we only prefer calcium and magnesium because their concentration is greater than the compared to the other elements. That's why we prefer them. Okay, as the concentrations of calcium Ca plus 2 and magnesium Mg plus 2 are usually greater than other alkaline earth ions group 2. So now detect the hardness, we use this equation Ca plus 2 plus Mg plus 2, 2. Okay, yeah. Now next point, the amount of dissolved calcium and magnesium in water determines how hard the water is. See, we take major compounds as magnesium and calcium, right? So when we are dissolving the magnesium and calcium into the water, the amount of magnesium and calcium is dissolved that determines the hardness of the water. Okay, so if for example 20 to 30% of the magnesium and calcium is dissolved in water, then that particular amount is determines the hardness of the water. The amount of dissolved calcium and magnesium in water determines how hard the water is. Okay. Now let's move to the next slide. Yeah. Water hardness is typically classified into four types: soft 0 to 0.6 mole per liter, then moderately hard 0.61 to 1.20 mole per liter, then finally hard 1.21 to 1.80 mole per liter, and very hard, which is 1.81 mole per liter. So typically the water hardness is classified into four types, as we have seen. One is the soft, one is moderate and hard and very hard. So the for soft, we can see that 0.0 to 0.6 mole per liter. If the concentration is 0.0 to 0.6, then we can say the water is softer. If the concentration of water is 0.61 to 1.20 mole per liter, then we can say that it is moderately hard. Okay. But when it comes to the concentration like 1.21 to 1.80 mole per liter, we can say that it is hard. Okay. And if the concentration exceeds to the 1.80, for example, it comes like 1.81 mole per liter, then we can say that it is very hard. It is very hard. For example, a big portion of Great Plains and Mountain West in the US has very hard water, while the majority of the Southeast US has hard water. So here we can see an example that a big portion of Great Plains and mountains in the west of the US has very hard water. So the hard water, it means that in plains and mountain in the west side of the US has the concentration of 1.81 mole per liter. That's why the water is very hard. So here we can see one more example also. Yeah. While the majority of Southeast US has hard water. Yeah. See, in here the example shows that in plains and mountain in the west side of the US, it has very hard water. When, when compared to the southeast side of the US, it has just hard water. It means in the southeast side of the US, it has only 1.80 mole per liter. But in the west side of the US, it has very hard water. That is, the concentration is 1.81 mole per liter. Yeah. Now let's go to the other slide. Yeah. Hard water creates spot in glassware, build up spots, rings around bathtub, and reduces efficiency of soap and detergents. So we all know that hard water create spot in glassware, build up spots, rings around bathtub. You can see in the bathtub, while we continuously flow the hard water, we can see some spots or rings also we can see. Yeah, that is because of the hard water. And the efficiency of the soap will also reduces due to the hard water. So, and one more thing, the efficiency of soaps as well as the detergents. The efficiency of the detergents also reduces. So here, besides this hard water also, clogs pipes from household to industrial. Yeah, As I told you before, it is a big concern of the hard water for the domestic and the industrial sorry, for the industrial purpose. So here, the hard water, what it does is nothing but when flow from the pipes, no, it clogs the pipe. It means some blockages occurs due to this flow of the hard water. Okay, and yeah, spots rings around the bathtub, and it also creates spot in the glassware. Okay, and reduces the efficiency of soap and detergents, as I told you earlier. Then besides this, hard water also clogs pipes from household to industry. Okay, yeah. Now let's move to the next slide. Yeah, this is a picture of concentration of hardness as calcium carbonate in milligrams per liter. Okay, yeah. Concentration of hardness as calcium carbonate in milligrams per liter. Yeah, so now you can see here 0 to 60. 0 to 60. This is the concentration in this area. In this area, this is the concentration. It means it is not, the hard water is somewhat less. Okay, yeah, in this area, the hard water is somewhat less, and 60 to 120 in this area. Yeah, in this area, in this area, the concentration of hardness of the water is 1 to 120. 1 to 120 in this area. Okay, yeah, yeah. Next, here 121 to 180, the concentration of hard water is 121 to 180. Yeah, in this white area, white colored area, you can see over here. Yeah, the white colored area, the hardness, the concentration of hardness of water is 121 to 180. Okay, yeah. And the very hardness of the water, it means the hardness of the concentration of hardness of the water is more in this red color region. Yeah, you can see over here. Okay, yeah, here 181 to 250. I will repeat it again. The concentration of hardness of water is lesser in this area. Yeah, this is the dark blue color area, you can see over here. It is just 0 to 60 only, the hardness of the water. Okay, the concentration of hardness of water is only 0 to 60 in this dark blue colored area, and little bit increase in this light blue colored area, that is 1 to 61 to 120. The concentration of hardness of the water is 61 to 120 in this light blue colored area, and the concentration of hardness of the water is 121 to 180 in this white colored area, you can see over here. Yeah, and then the concentration of hardness of the water is 181 to 250, which is maximum in this red colored area, and this red colored area you can see over here. Yeah, this is concentration of hardness as calcium carbonate in milligrams per liter. Okay, not mole per liters, it is milligrams per liter. Yeah, now we'll move to the next slide. Yeah, this is the some explanation regarding how we detect the hardness of the water. Yeah, in before slides we have seen what are the elements we use to detect the hardness of the water, and what are its consequences, and the percentage, the concentration of the hardness of the water we have seen, and the disadvantages of the hardness of water we have seen. Now we'll uh, see the explanation regarding the how we detect the hardness of the water. Okay. Calma guide. A metal ion indicator changes color of a solution to wine red in presence of calcium Ca plus 2 and magnesium Mg plus 2 ion at pH 10. Yeah, so Talmagite is a metal indicator, okay, which changes the color of a solution to the red in presence of calcium and magnesium at pH 10. Okay, now ethylene diamine iterate acetic acid EDTA, which is called as, displaces the indicator from the metal indicator complex after it is added to a solution and turns it blue. So when this EDTA is added to the solution of Ca and magnesium, and then it turns blue color. When calmagite is added to the solution of magnesium and calcium, it turns red. But when EDTA is added to the solution of magnesium and calcium, it turns blue. Okay. Yeah. Now we'll go to the next slide. A red solution is transparent to a red light, whereas non-transparent to a blue light, and vice versa. Okay. A photodiode placed across the solution will give out a reading of voltage variation across the diode depending on the amount of red or blue light passing through the solution and starting the photodiode. Okay. Yeah. A sensor prototype is 3D printed with a channel embedded in it to hold water sample. It is a sensor prototype which hold the water. Okay. Water hardness is detected based on visual inspection of color change of the sample and voltage change occurring when calmagite and EDTA are mixed to the sample. So water hardness is detected. We can check the water hardness by its color. It means in the previous slides, as I have shown you that when the calmagite is added to the solution of calcium and magnesium, it changes to the wine red color. Okay, the wine red color is also detects the hardness of the water, whereas the EDTA is also added to the solution. It gives the blue color. Then we can detect the hardness of the water. Okay, yeah, this one. See, here in this picture shows that red color solution after calmagite is added. See here, when calmagite is added to the solution of magnesium and calcium, it gives wine red color, as we have discussed in the previous slide. So, okay, and then EDTA. When EDTA is added to the calcium and magnesium solution, it gives blue color. Okay, and this is the first generation of 3D printed prototype. Now we'll move to the next slide. For a first generation prototype, voltage variation of 30% and 13% for a blue light and 6% and 74% in average for red light. So the voltage variation of 30% and 13% for the blue light, and for the red light it is 6% and 74%. Okay, now in comparison to the baseline, when neither calmagite nor EDTA is mixed to the water sample is observed due to color change. Okay, when neither calmagite or EDTA is mixed to the water sample is observed due to the color change. Okay, then a second generation prototype is printed, which shows improvement in voltage readings compared with the first generation. As in the first generation, we have seen that the voltage is 30% to 13%. But in the second generation prototype, which shows improvement in the voltage readings, it means the readings of the voltage have been improved in the second generation compared to the first generation. So transmittance and absorbance of the solution are computed using the voltage variation data recorded across the photodiodes. A calibration curve is then compiled by measuring absorbance of various concentrations of standard CaCO3 solution, which is then used to predict the water hardness type of the water sample. Here, a calibration curve is then compiled by measuring absorbance of various concentrations of standard CaCO3 solution, which is used to predict the water hardness. Okay. Now, yeah, this is the curve of the calibration as we have discussed in the previous slide. Yeah, the calibration curve is then compiled by measuring absorbance of various concentrations. Okay. Now, this curve shows you a compiled measuring of absorbance of various concentrations of CaCO3 solutions. Okay. Uh, a total hardness concentration mole per liter in terms of CaCO3 solution. See here, this is a linear fitting. Okay, this is the absorbance. Red color one is the absorbance. Okay, yeah, this is the linear fitting. Yeah, you can see here it is on the 0.15. Yeah, it goes on increasing onto the 0.2 also. Yeah, this is known as the calibration curve. Okay, of CaCO3 in terms of CaCO3 solution. Now, this is a table uh, when the when the calmagite is added to the solution of the magnesium and calcium, and when EDTA is added, the percentages of the blue, red has been shown, and the transmittance percentage as well as the absorbance also has been shown to you. Yeah, once we'll go through it. Water pH 10 buffer, calmagite water pH 10 buffer, calmagite EDTA. In transmittance, the blue percentage is 78.848, and EDTA transmitters percentage is in blue color. EDTA transmitters percentage is 86.409, whereas the calmagite transmitters percentage in red color is 92.509, and in EDTA transmitters percentage in red color is 50.127, whereas the calmagite absorbance in the blue is 0.104, and EDTA absorbance in red color is 0.034. And then here, water pH 10 buffer calmagite, water pH 10 buffer calmagite EDTA. Here the transmittance percentage in blue is 70.039, and in EDTA 86.529, and in red it is 93.881 for the calmagite. For EDTA it is 25.618 in red color. Okay, and here the absorbance, calmagite absorbance in blue color it is 0.157. Okay, in red color calmagite absorbance it is 0.027. EDTA absorbance in blue color is 0.063, and EDTA absorbance in red color is 0.616. Here, calmagite pH 10 buffer, calmagite transmittance percentage in 70 in blue color it is 78, and EDTA it is 88%. In red color, calmagite is 92 and EDTA is 40.81. Okay, yeah. In calmagite absorbance in blue color it is 0.104, and red color 0.032, and EDTA absorbance in blue color it is 0.053 and red 0.414. This is the table of the transmittance percentage of cal- calmagite when it is added in the blue, sorry, calmagite in blue color, calmagite in red color, EDTA in blue color, EDTA in red color. Okay. Yeah, thank you very much. This was the presentation on the fluidic colorimetric sensor, which is designed for the detection of hardness of the water. And I hope you understood the concept. Uh, Thank you.